Hello, my name is Lukas Weber, and this presentation is about exploring order-to-order transitions of Dirac fermions in the regime of strong interactions. So, if we talk about order-to-order transitions, there is one prominent example. This is the 2D spin-1/2 antiferromagnet. There we can have different ordered phases, like the Néel state or the valence bond solid. And the question is, what happens in a phase diagram when they are next to each other? And if we turn to Landau-Ginzburg-Wilson theory, the prediction is that there can be no direct continuous transition, but either an intermediate phase or first order transition. But there have been some more exotic proposals about the so-called deconfined quantum critical point scenario, where there is a direct continuous transition and further more emergent symmetries. The natural question is if we can get this not only in spin systems but in more complicated systems too. And in fact, there have been some interesting numerical studies for interacting Dirac fermions recently. And as always, the question is this a genuine deconfined quantum critical point, or can we find different explanations for it? And how does one go about constructing such a model that has Dirac fermions and an order-to-order transition? It can be done quite constructively by starting, for example, with the honeycomb Hubbard model. This gives us fermions with a Dirac cone and also one of the ordered phases, namely the antiferromagnet of the Hubbard model. And then for a second order, we want to add something more, so we can add Ising spins on the bonds of the lattice. And we want the two phases to be next to each other, the two ordered phases. So we want to make them competing in some way. And this can be done by coupling the two models, the Ising spins and the fermions, in a specific way. For example, by choosing such a Kekulé pattern. With this coupling, which couples the Ising spins sigma z to the fermions c dagger c. The hopping is staggered in such a way that if the Ising spins order, then the fermions will form a Kekulé valence bond solid, and this in turn destroys the antiferromagnetic order. In fact, this model has been proposed by Sato et al., and here you can see the full Hamiltonian. We have the normal Hubbard model with hopping and interaction term, and a transverse field Ising model with a transverse field that lets us switch on and off the order of the Ising spins. And then the two models are coupled by this interaction term from a previous slide. Now what they did was the two-dimensional quantum Monte Carlo to find the ground state phase diagram of this model, and they find three phases. First, there are the semi-metal and the antiferromagnet, like in the normal Hubbard model. And then for low transverse fields, you also have the Kekulé valence bond solid phase when the Ising spins order. From the analysis, it looks like there is a direct continuous transition between the antiferromagnet and the KVBS phase. And what's also interesting is that they find emergent O4 symmetry at this transition at u equals 6. So these are all hints that this could be a deconfined quantum critical point. However, we need to be more careful because this analysis is based on very small system sizes. So for a definite answer, it's important to get a more accurate view of the situation. And how can we do that? Well, we note that the region of interest here with this apparent direct transition is in the large U regime. And there, we may be able to use an effective spin model to describe the situation. And as you may know, the Hubbard model, if you turn up the interaction at half filling, eventually the charge gets frozen out and you wind up with the Heisenberg model. And it turns out in the if you have a Hubbard model and an Ising model, at first order at least, you get a Heisenberg model and an Ising model for large interactions. So the Hamiltonian looks like this. The transverse field Ising part of the model stays the same, and the fermions are replaced by Heisenberg spins. The great advantage of having this model now is that we can use stochastic series expansion quantum Monte Carlo, which is much more efficient than the methods you can use for fermions in this case. So then we do simulations, and we have now two order parameters. One is the staggered magnetization of the Heisenberg spins, which identifies the AFM phase. The other one is the magnetization of the Ising spins, which is the order parameter of the KVBS phase. Here you see the Binder ratio of these two order parameters in green and blue, and as a function of the transverse field for different system sizes. At a critical point, the Binder ratio crosses for the different system sizes because it has no scaling. And as you can see here, we don't get one crossing, but two distinct crossings. So actually there is not just a single critical point, but an intermediate phase where both orders exist, not a direct transition. And there's an alternative way to get estimates for the position of this of these two phase transitions by looking at the scaling behavior of the order parameters. If we plug in the critical exponents, we can draw the power laws in these red dashed lines that they should follow at the critical point, and then compare this to our simulations for different fields. And then the fields that are closest to this power law decay give us an estimate for the critical fields. And here you see this done for both the Heisenberg magnetization and the Ising magnetization. And again, we see two separated fields that are also consistent with the analysis of the Binder ratios. So this gives some strong evidence for an intermediate phase, but some questions remain. For example, what about this enlarged symmetry from the fermionic model? And what about other symmetry groups? Is it just this model, or can we make a more general statement? And in order to tackle these questions, we want to treat it on a more generic field theory level. So in a simple field theory, how can we describe what we just did? So we had Dirac fermions coupled to two order parameters, which we call here phi and chi. And those two bosonic order parameters transform onto different symmetry groups, ON1 and ON2. Now, we can try different values for N1 and N2, and the case from the QMC data is also part of this if we choose N1 equals to 3 and N2 equals to 1. So that's the AFM and the KVBS. But in general, we can use the functional renormalization group to find the phase diagram of this field theory. This is what you see here for some different values of N1 and N2, and it turns out that there are similarities for all the different symmetry groups. You always have the intermediate phase between the two ordered phases, and also this multi-critical point in between the Dirac semimetal and all the other phases has a special property. It has an emergent ON1 plus N2 symmetry, which would explain what they measured in the fermionic data, because that was actually rather close to this multi-critical point. Now, if we put this next to the QMC data, we see, of course, the phase diagram in the large U limit further away from the Dirac semi-metal. And then we only see the two ordered phases and the intermediate phase. So in summary, we find this multi-critical point with an emergent large symmetry. And this, together with an intermediate phase, seems to be a generic result for interacting fermions, Dirac fermions coupled to two order parameters. We were able to confirm this in a microscopic model and found a previously unresolved intermediate phase where both orders exist. And this was not found in the fermionic Monte Carlo because they only looked at small system sizes. We were able to overcome this by using an effective spin model instead. If you want to find out more about the details of both the quantum Monte Carlo simulation and the FRG, you can look at a paper that's on the archive. Thank you.